So we want to keep on going with dynamics and forces, but let's just warm up with a little question first. I'm just going to draw a little road like that. I'm just going to draw a car. There we go, couple wheels. There we go. There we go. All right, something simple. Okay, so here we got a basic little car. Let's say our car is 1,600 kilograms and it's driving along at 3.2 meters per second. And it's going to speed up because, of course, the engine is going to supply a force. And let's say that the car goes... let's say the car goes 65 meters and it reaches a speed of 12.4 meters per second. And I want to know what is the force applied for the engine. Okay, so let's just start with some simple things that we can find here. I've got speeds, I've got distance. So we can piece a few things together here. Let's see. Well, this is my first V. That's my second V. I'm just going to work with my V's first. Well, I got my first V and I've got my last V, so I can find my change in V. My change in V, of course, will come in handy for finding something like acceleration. So my change in V was 9.2 meters per second. I'm also going to find my average V. Can come in handy too. So I'm just going to find my average V, which of course is halfway in between. And my average V is 7.5. So I've got all my V's laid out, which they often come in handy. All right, so let's see what else we got going on here. Well, I've also got the distance. Well, with distance and average V, you got distance and average V, I can find the time. So time would be the distance divided by the average V. So I can take that 65 and I can divide that by the 7.8, which gives me an average V of like 8.3 seconds. Well, now with that, I've got my time. I've also got my change in V. Of course, the change in V in time, I can find my acceleration. So, of course, acceleration would be change in V over change in T. So I'll take that 9.2 and divide it by the time that I just found of 8.3 seconds and get an acceleration of like 1.1 meters per second squared. Okay. I've got my acceleration. I've also got my mass. My mass is right there. So I got my acceleration. I've got mass. And those two things put together will give me my net force. Now, I have no other forces. I'm not worried about friction or anything going on like that, blah, blah, blah. The net force is the only force that we have, which is the applied force. That's all we're worried. That's the only force we got. So no big deal. The net force is going to be MA. So I'll take that 1.1, just times that by the mass of the car, which gives me a force of about 1770 newtons. And again, that would also be the applied force because I got nothing else going on at all here. Okay, so let's incorporate a little more here. Let's build on this a little bit and adjust the situation. So suppose there's mud or something like that here. I'll draw some mud, blah, blah, blah. There's some mud. Okay, so let's say we end up with 400 newtons of mud resistance. Okay, so maybe we're going to incorporate 400 newtons of mud resistance. If that was true, what would the new final speed and distance be now? Okay, so let's sort of like just take the exact same question, just sort of work it the other way, incorporating some mud. Okay, well, I know that my engine is supplying 1770, so I can start with that. I know the engine is supplying 1770, but now I've got 400 newtons of mud. So this is where I would say, my applied force is 1770, and the first part, that was my net force, but not anymore. My net force this time is going to be that 1770 that the engine is pushing with, subtract the 400 newtons from the mud, which leaves me with only 1370 newtons. So now I've only got 1300 newtons of net force, which of course is going to change my acceleration. So now my acceleration is going to be that net force divided by mass. And before my acceleration is 1.1, it's going to go down a little bit because I got less net force. So I'll just take that 1370 and divide that by the mass of the vehicle. And now my acceleration is down to like 0.86 meters per second squared. Okay, well, now that I have that, we can sort of try and incorporate some other stuff. Things will change, obviously. Well, we'll just use the exact same time we did before. Let's just keep the exact same amount of time and make things easy. So our new change in v would be the acceleration times the time. So I've got that 0.86. I'm just going to use the same amount of time as before. And if I do that, my change in v is now 7.1 meters per second. So before it was 9.2, but the mud's going to slow it down, so now it only went up to 7.1, or it went up by 7.1. So now I can use that to figure out my final v, because I know my car started at 3.2, that hasn't changed, and then it went faster by 7.1, so now my new final speed would just be the 3.2 we started with, plus the 7.1. We just have to add the two together, and we're looking around 10.3 meters per second. Okay, so the car went from 3.2, it changed by 7.1, so it ended up at 10.3. Okay, well, now we can also find out the new average speed. The new average speed would be in there as well. So we'll take that 3.2, add it to the 10.3, add those up, divide by 2, and we're looking around 6.8 meters per second for an average speed, which I can then use for my distance calculation. So if I get, it's different green, that one right there. If I do DTV again, so my time, again, I'm just going to keep the 8.3 for my time. I'm not going to change that. And I'm going to use my new average V of 6.8. So I'll multiply the 8.3 by the 6.8, and it gives me a distance of around 56 meters. Okay, and that's it. So sort of like the same question, sort of twice, with a slight adjustment with the mud, but one part we started with some kinematics and worked our way to the dynamics part, the forces. And then the second time we sort of did pretty much the exact same steps in reverse. We started with forces and then worked our way back to the basic kinematic quantities. Okay, all right, so now that we've done that, we're going to start looking at some other force stuff today a little bit, and show you an application of another really common force. So we'll clean this up and then we'll keep on going with some other stuff. All right, so now we're going to start talking about a very special common type of force, and where this sort of kicks in is often the classic thing of mass versus weight. And mass and weight are not the same thing. The terms are often used interchangeably, but they're not the same thing. And when you actually start taking Newton's laws, it really helps to define the difference between the two. Now, for mass, when we look at mass, mass is actually connected to law number one. It's connected to the idea behind inertia. That's law number one is heavily connected to mass. It's all about inertia and stuff like that. Mass basically is about how hard it is to accelerate. Okay, so that's sort of is the key right there. How hard is it to accelerate? If you got like two boxes which look exactly the same sitting in front of you, how do you know which one's heavier? Well, you try and move them, and when you try and move them, you can tell which one's heavier because it was harder to accelerate. It has more mass. And of course, mass doesn't change no matter where you are. Your mass is always going to be the same, whether it's here or on the moon, in space, it doesn't matter. If you are harder to accelerate on Earth, you will also be harder to accelerate in space. You'll be harder to accelerate on the moon. It doesn't make any difference. And that's what it is sort of mainly connected to, is inertia. That's how I like to think of it. Now, weight, on the other hand, is a little bit different. Very simply, weight is a force. That is basically it. Weight is a force. More specifically, it is the force from gravity. It's the, it's the more the common term for the force due to gravity. That's what it is. So mass has to do with how hard it is to accelerate. Weight is actually the force used by gravity to accelerate something, right? So mass, it has to do with law number one. Okay, that's sort of what this is here. This is like law number one from Newton. This one here is a force. This is actually law number two. So that's sort of like the key difference between the two. So weight is law number two, which is just basically F equals ma. But we can specialize this if we're talking about the force from gravity mass is the object, but then we need to use the acceleration due to gravity. And that's basically it. Now, of course, the acceleration from gravity, especially in Earth, is such an unbelievably common value. It gets used all the time. And because of that, it gets its own little symbol. It's a lowercase g, which, of course, is around 9.81 meters per second squared, which you guys may already know from other stuff that you guys have done. So the force of gravity, or the weight, is a really, really common force. Gravity causes things to move, speed up, slow down, it causes pressure, a whole bunch of stuff. Force of gravity is really, really common. And it's basically just take the mass, which is like the inertia part of it, and multiply it by the acceleration from gravity, and you've calculated the weight. So, of course, mass doesn't change, but the weight does, because depending on the acceleration due to gravity, you will weigh more or less. So, when you go to the moon, the acceleration due to gravity is less, about 6 times less. You will weigh about 6 times less, but your mass would be the same, right? So that's sort of the key right there. Mass is about law number 1, inertia, how hard to accelerate. Weight is law number 2, F equals ma, and depends on both mass and gravity. Okay, so we're just going to look at some really, really common scenarios that kick in for this type of thing and incorporate some gravity. Now, what's kind of interesting, of course, most people know, like, the whole 9.81, I mean, that's how fast you accelerate when you fall. It has nothing to do with mass. The weight has to do with mass, but not your acceleration. Your acceleration, everything, if you don't bring in drag and air resistance and that type of stuff, everything falls at the same rate. Everything falls and accelerates at 9.81 meters per second squared when you're not including drag and that type of stuff. Okay, but we'll worry about some of that stuff maybe a little bit later on. Okay. So let's look at some basic scenarios, some classic physics scenarios where the force of gravity is used to move different things, okay? Now there's a couple really, really common classic scenarios, but let's just start with the simple one here. One of the classic ones is maybe something like this, and we're going to draw a circle, something like that. That's a pulley. And then I'm going to connect it like this. There we go. All right, we're so super classic. And, we're going to do some wheels here, some wheels. Okay, we're going to put a box on here. Something like that. We're using wheels because we don't want to have to worry about friction at all. We're not going to worry about friction right now. That we can take care of later on. So we got a red box and, red box. And we're also going to draw another box over here. Oh, we'll change that to a blue one. There you go. Okay, so we got a red one, got a blue one. Oh, we can even color those in. Ooh, there we go. There we go. And then I'm going to connect them with a rope. There you go. Something like that. Okay, good. So this is one of the most classic, common type scenarios, basic forces and stuff like that. Gravity, pulley, one thing pulling something else, blah, blah, blah. Okay, so let's look at some values here. Let's say we've got a, let's say this one right here. Let's say this is a 16 kilogram box. And let's say this over here is a 12 kilogram box. Okay, now I want to know what's the acceleration of the system. Okay, super classic. Now, when I look at the two boxes, the red box and the blue box, which one is pulling? Okay, and that's one of the things I'll often ask myself when I do questions like this. What is pulling? What's slowing down? So if I look at what is pulling, is the red box pulling or the blue box pulling? Well, think about it this way. Take, right there. Let's take an eraser here. If I would cut the rope right here, if I cut that rope right there, what would happen? Well, the pink box would just stay there. The blue one would fall. So the blue one is the only one that's actually pulling, and it's pulling because of gravity. So let's reattach that. So the blue one is the only one that's actually applying a force. So this is the one that is actually applying a force. And of course, it's applying a force because gravity is pulling on it. So I want to find out how much gravity is pulling on it, and that is just the mg for the box. That's that expression right there. So if I take that 12 and I multiply that by 9.81, I get around, round off, get 118 newtons. So that box the gravity is pulling on that box with 118 newtons, and that is how much the blue box is pulling on the pink box with. So that is the force that is applied to try and move everything. Okay, so in this case, that mg, that 118, that is the applied force. Okay, so I've got 118 newtons trying to move it. There's nothing else pulling on it. So my force applied is coming from my mg, and it's 118 newtons. Okay, is there anything try to slow it down? Well, no, there's no friction, there's no nothing, blah, blah, blah. There's nobody pulling on it the other way. That's the only force trying to move it. Okay, well, if that's the only force trying to move it, to find the acceleration would be the net force divided by the mass. And since the 118 is the only force we've got going on, not only is that my applied force, that's also going to be my net force because I got nothing else working on this thing. So my net force would also be 118. Okay, so now I want to divide that by the mass. Now, what mass do I use? Well, what's moving? The blue box is moving, but the pink box or the red box is also moving. So they're both moving. So I want to use the total mass altogether because they're both moving. So I'm going to take that 118 newtons and divide it by the total mass of 28. So if I do that 118 divided by 28, I get an acceleration of about 4.2 meters per second squared. And obviously it would be going around something like this. Okay. So this where the mg is actually a whole, it's the force of gravity in the box, it's the applied force on the boxes, and also ends up being the net force because we didn't have any other forces acting on the situation. Okay, well, how about if let's modify this a tiny little bit. Okay, what if here we'll do a little divider here. Let's say on the box, the pink one, let's say a wheel broke on the box. I mean, the wheel wasn't working very well. So because of that, there's 25 newtons of friction. And let's do the exact same thing. So let's say one of these wheels, maybe that wheel broke right there, and it's applying 25 newtons of friction. What would the new acceleration be? Well, a lot of this would actually be very similar. The 118 is still the applied force. That's not going to change. My applied force is still 118 newtons from that mg that I found over there. No difference. That's how much is trying to pull it. And that's what I often ask myself is how much is trying to move it? And then I ask myself how much is trying to slow it down. So how much is trying to move it? Well, 118 is trying to move it. That hasn't changed. Well, is there anything trying to slow it down? Well, before there was nothing trying to slow it down. This time there is. I've got 25 newtons of friction slowing it down. So my force of friction, which is FF, is 25 newtons. Well, if I've got 118 trying to move it, and friction is 25, slowing it down, I'm going to take those two and I'm going to subtract them. And that will then be my net force. So my net force would then be the difference between the two, which would be 93 newtons. Okay, so now my net force is only 93 because I got to subtract that friction. Well, now the rest is very similar to before. Acceleration is net force divided by mass. So this time I'll use the 93. Total mass has not changed. That's still 28. So I'll take that 93 and divide it by the 28, and I get around 3.3 meters per second squared. Okay, and that's how it pieces together. So there's no set steps. You got to look at each situation. And I always ask, I have for cajillions of years, I always ask myself, what's trying to move it? What's trying to slow it down? Sometimes there's nothing slowing it down, sometimes there is, and then I piece things together. So every situation can be a little bit different. The steps are often similar, and there's similar, things here and there. We want to look at each situation specifically on its own. And again, what's trying to move it? What's trying to slow it down? I often ask myself, what's pulling it left? What's pulling it right? And there's another way to do it. That's another way to look at it. Okay, so let's do a couple more types of questions using forced gravity and a couple other classic scenarios and work with it a little bit more. All right, so another super classic type scenario to practice gravity type stuff is another pulley type thing, except we are going to have two things hanging on it. So let's get a little rope or something like that. There's one, something like that. Again, let's just use boxes for now. Oops, wrong color. Oops. Try that one again. Rope. There we go, something like that. Good. Okay, then we'll draw a couple of boxes on here. Box. I'll make that one red again. Make another box. There, something like that. Make that one blue again. Ooh, let's fill them in. Fancy blue color, fancy pink color. There we go, something like that. Okay, so let's get some masses in here. Let's say this is 35 kilograms, and let's say this one is 28 kilograms. Okay, so I'm going to find my forces of gravity. I know they're involved. I'm going to find them, just get them out of the way. I'm going to find the mg for this box, the force of gravity for that box. So it's really easy. It's 35 times 9.81. And that's around 343 newtons. So I'm just going to do the same thing for the blue one. mg is equal to 28 times 9.81. And the weight of that one is going to be around 275. Okay, so there's my two forces of gravity. I know they're involved, so we'll piece it together that way. Okay, so what I want to do is I want to find out what is the acceleration of the system. Okay. So what I'm going to do is the same thing I did before, and this is what I like to do, is I ask myself, what is trying to pull, what is trying to move it? Okay, now if I cut the rope, both of them would fall, which means they're both pulling. They're both trying to move this thing. Now I've got that red one is pulling with 343, trying to move it this way. And I've got my other one, the blue one's pulling with 275, trying to move it this way. Well, since they're trying to pull in opposite directions, obviously I'm going to have to subtract those two. So I'm going to take that 343 and subtract the 275. And if I just subtract those two values, I'm left with like 68 newtons, and the system would try and rotate towards the left. So that right there, that would be my net force. This is, this one right here, that's like an applied force, a force of gravity, but it's an applied force. So is this one. I put my two applied forces together. So, you could call this, I would often call this my total applied force, which also would then be my net force in this case. So I've got my net force, and I'll do very similar as before. Acceleration is net force divided by mass. So I would take that 68. Once again, I want to use the total mass altogether. I'm going to use the combination of 35 and the 28 put together, which is 63 kilograms. So if I do that 68 divided by 63, that gives me an acceleration of about 1.1 meters per second squared towards the left, or rotating towards the left. Okay, so like we did before, let's adjust the situation a little bit. Maybe there's a little rust in the, got some rust in the old pulley here. So it got some friction problems, squeaking a little bit. So let's incorporate some friction into here. Suppose we got 30 newtons of friction in the pulley. Okay, so what would the acceleration be now? Okay, well, same type of thing as before. There's not much difference here. I would still need my mg's, which I found at the beginning. That's no big deal. My total applied force is still going to be 68 newtons towards left. That's fine. So that's how much is trying to move it. So naturally, what's trying to move it? That's what I asked myself. Now, is anything trying to slow it down? Well, before, no, but now I've got friction. How much is trying to slow it down? I've got 30 newtons of friction trying to slow it down. So I've got 68 trying to move it, and I've got 30 trying to slow it down. So I'm going to subtract those two, and when I subtract those two, that would tell me that my net force is going to be 38 newtons, and it's trying to go to the left. Okay, so once again, how much is trying to move it? Put those together. I like to get my total applied force, and then I ask myself, what's trying to slow it down? In this case, there's 30 newtons trying to slow it down. Then I would put the two together, get the whatever's left over, which would then be my net force. And people have different ways and labels they like to use, but this is the way I like to set it up. Was trying to move it, was trying to slow it down, put them together. Okay, all right, so my net force was 38 newtons. So now that I have that, my acceleration is going to be F net divided by the total mass again. I'll put a little t there for total. My net force is 38, so I'll take that 38 and divide it by the total mass, which is again 63 kilograms. That hasn't changed. So divide that by the 63, and now we're looking around 0.60 meters per second squared towards the left. Okay, so very similar to the other one, just two forces trying to move it instead of one force. So this time, I can incorporate the total applied force, and then, get the total applied force, subtract friction if there's some friction, divide by total mass if needed, and then that's about it. And then you could use VAT and a whole bunch of other stuff as well. Okay, so there's another really common type of basic force of gravity type thing. Often pulleys and boxes are really, really common. Okay, so we'll clean this up, and then I'll show you one more other really common type of gravity type scenario. So another super common scenario we can look at. Let's do this, something like this. Right, and let's give it a little bit of color in there. There we go. Oh, so there we go. So another really common type of thing that kicks in with this type of stuff is when things are hanging. And look, there we go, something like this. Oh, that's triangle. Something like this. Okay, so suppose we've got, oops, wrong one. All right, so suppose we've got a person hanging on a rope. So things hanging on ropes and stuff like that often kicks in. And this is where another really common type of force kicks in, and that's the idea behind tension. Like tension is force that's contained within a rope or a chain or something like that. Most people think about ropes and stuff like that when things are pulling on them. And of course, there'd be, because he's hanging on there, there's tension up there. There isn't really any tension down here, but there is tension on the top because he's hanging on it. So let's sort of look at this a little bit. So let's say we have a 65 kilogram person, and let's just say they are at rest. What would the tension be in the rope? So what's the tension of the rope? Well, why is there tension on the rope? Well, because gravity's pulling on the guy. So, I mean, no big surprise, we need to find his force of gravity. We need to find his mg. And if we find his mg, there's about 638 newtons. That's his weight of 638 newtons. And that would then be existing within the rope up there, because obviously if he let go of the rope, if all of a sudden he fell, there'd be no tension in the rope. So just that alone, that would be 638 newtons, and that's it. So really, really, really easy. Okay. Here, let's clean up this part down here. There we go. Complete. So 638 newtons of tension at the top. And below him, there would be nothing. There's no tension below him. It's just above him. Now, it's really, really common, when people are on ropes, either climbing up or climbing down. And if he would do one of those two things, it can actually change the tension. So maybe he will actually slide down, accelerating at 1/2 meters per second squared. So what would the tension be now? Well, when you slide down the rope, you're letting go of the rope, you release your grip a little bit, and you actually relieve some of the tension above it. The tension will actually go down. The exact opposite happens, obviously, if you're like climbing up a rope. When you're climbing up a rope, you're yanking and you're pulling it all the time, climbing up, you will increase the tension. So when he slides down and accelerates at 1.5, the tension, which is what we're looking for, it is actually going to decrease. There's actually going to be there's less tension. Well, how much less? Well, I've got his mass and I've got an acceleration. Let's just put those two together. If I did F equals ma, if I do that 65 times 1.5, we'll just round off. We get 98 newtons. that 98 newtons is being used to move him. That's his acceleration right there. That's being used to move him. Well, gravity's pulling on him with 638 newtons. About 100 of it is being used to move him. So where's the rest? Well, the rest must still be tension in the rope. And you're not sliding down very fast, okay? You're only accelerating at 1.5. I mean, if you let go of the rope, you'd be accelerating at like almost 10, like 9.81. So that is actually, oh, look, a bell from school. There we have a 1.5 meters per second squared. It's not a lot of acceleration. So it's only going to reduce the tension a little bit. And it's only going to reduce it apparently by 98 newtons. So all I'd have to do is do the 638 and subtract the 98, and we'd be left with 540 newtons. So that would be the new tension in the rope. Okay. Now, what if we, what if we sort of reversed it? What if he climbs the rope? He climbs and actually accelerates at 1.5 meters per second squared going up the rope. Well, if he climbs up the rope, he's going to increase the tension. There's going to be more tension on it. So we would just have to slightly adjust it a little bit. So instead of subtracting it to give us less tension, we would add it. We'd start with the 638. Okay, we're going to start with that 638. That hasn't changed. So we've got the 638 newtons. But instead of subtracting the 98, we are going to add the 98 newtons because there's going to be more tension on the rope. And if we do that, we've got 736 newtons would be the new tension. Okay, so you just got to think about it, and you got to sometimes think about the situation. If he's just at rest, if he's just sitting there, the tension is 638. If you slide down the rope, accelerating at 1.5, you're going to reduce it by your F equals ma. If you climb up the rope, you're going to increase the tension, and you're going to increase it by the F equals ma. So you get more or less tension. Now, what if instead, what if he slides down the rope, he slides at a constant speed? Well, if he slides at a constant speed, there's no extra acceleration. Since there's no extra acceleration, there's no change in the force. So there is no extra acceleration. So the tension would just stay at 638 newtons. In order to have more or less tension or force, you need to have more or less acceleration. So this is where you'd be sliding down a nice constant V, no acceleration whatsoever that's extra. The tension would just remain at the 638. Okay, so 2 boxes with a pulley, one on a table or something like that, one going off the edge, a double box pulley type question, and tension ones are all really, really, really common basic force of gravity type situations.